it is, yeah, it is
How's
also a
that?
great pleasure to have you here. Barry is an expert in quantum optics and in atomtronics, and he has given remarkable contribution to atom trapping ideas. So thank you very much, Barry, and please, the floor is yours.
Thank you, Anna, and thank you very much everyone who's involved in organization for a great conference, and thank you for the invitation to speak here. I hope you can hear me okay, and it's very hot here, by the way, but I'm going to plow through this anyway as best as I can. And actually, so my original talk title is dressing cold atoms for rings and shells, and I will try and stick with that. But it's interesting coming in at this point in the conference that quite a few of the things that I wanted to say have been said already. So because RF dressing is very much part of the toolbox of creating quite interesting traps, which is something that is a requirement for atomtronics, different topologies and so on, and different connections. This is needed, and there's a role to play not just for optical potentials, but this kind of radio frequency approach, which is the sort of thing that I'm going to focus on. So the plan of the talk then is basically a very fast introduction to radio frequency dressing, in case there are people who weren't here last week, for example, because already Bohr von Klitzing and other people have mentioned this and given an outline. But I'll just cover the basic ground quickly. I'll talk a bit about matter wave bubbles and then a bit about traps. So the matter wave bubbles are the shells, and then we do a bit on the rings at the end. So let's go to the next slide. And this is essentially my conclusion point, really, by way of an introduction, which is to say that you know, the radio frequency potential is extremely versatile. I'm going to go a little bit under the hood and look at details of these, how it is these things work. But the outcome is all these different topologies like rings, double rings, double shells, lattices, and bubble states, which we will focus on a little bit in the talk. Just to mention here in this is almost like the conclusion, that there are all these different possibilities and more than I have included in this picture. Just to mention that if you get interested and want to be involved in this, then a good place to start is one of or both of these reviews. So this one is Journal of Physics B 2016, still good for starting. And this is an advances book article, which is harder to get for some libraries maybe, but there's a preprint on the archive from 2017 there. So let's get into the some of the detail. And this whole business is, I just quickly want to say, this whole business of radio frequency dressing is inspired by Cohen-Tanuji's approach to dressed atoms, which is actually a very optical approach. And technically it's different what we do here, what I'm going to talk about, because we do it with radio frequency and not with optical, so we don't really have spontaneous emission. And so, you know, this the quantum, some aspects of the quantum nature of these energy levels is lost. Nevertheless, there is an equivalence between Cohen-Tanuji's dressing and the sort of dressing that we're talking about here. Essentially, it's diagonalization of the right part of the problem. More about that in a Hamiltonian in a minute. This is just a reminder that for the typical atom, rubidium-87, then the Zeeman split levels are in the radio frequency range, and the difference between these hyperfine states, ground states here, is the microwave frequency that will get mentioned later. So you have microwave here, big gap, and lots of little radio frequencies. But I guess I don't need to say all that detail to this audience. And this picture has already been captured and done by at least Bohr von Klitzing. So this is my sort of toy, my favorite toy idea for presenting how the dressing works for those who don't know about it. So the idea is that here you have Zeeman split levels, but split is a function of space, and so that means then the atom on this lower state here, this is F equals 1, feels a gradient, so there's a force on it, so it moves, and then it moves down the slope, it gets into a region of resonance, and provided the field is strong enough that it's transferred up to this level, where it decelerates and eventually comes back, and it will oscillate backwards and forwards like that. I'm not sure if I can do, yes, I can do oscillation. So it goes backwards and forwards like that. Don't want to go too far, which means that it's trapped in this apparently unstable position. And I like this figure because back in about 2000, I was able to convince an experimentalist that maybe this could work, because really at the beginning of this story, it was not at all clear to people that it would be possible to trap atoms in this kind of unstable looking location of the RF resonance where the arrows are. And that was part of the obstacle of getting this thing going in the beginning. So we've seen the toy diagram already from probably both Wolfgang Klitzing and Romain Debussy from Paris. But why does it work? So as they've already talked about the basic setup, I can say a bit more then about why this works. And one approach to understanding what's underneath the hood is the Landau-Zener approach to level crossings. So you can regard the atom coming up to the radio frequency resonance as coming up on this slope, interacting here, and then passing through, and maybe coming out on this upper level, or coming out adiabatically on this lower level. And for an atom traveling fairly fast through this crossing, you can approximate this by this Landau-Zener Hamiltonian, which is really treating a classical trajectory for the atom. So you say, you know, the energy level difference between these energy levels is linear in time, and the slope here is governed by the trajectory of the atom. This model, if you take it exactly as given here, has an exact solution, which is one of the wonderful exactly solvable problems of quantum mechanics. An exact solution actually in parabolic cylinder functions, but what's really nice is the solution at infinity. The probability transfer, whether it's adiabatic or not adiabatic, is just given by a simple exponential involving the coupling squared, which would be like the RF Rabi frequency, divided by the slope, which is essentially the magnetic field gradient when it comes to radio frequency trapping. So this, in a way, explains the robustness and the strength of radio frequency trapping. It's because the probability of it not working is an exponential of a small, an exponential which is extremely small, because if you make this adiabaticity parameter very large, then e to the minus lambda is very small. And it's easy to make this adiabaticity parameter very large because you just crank up the radio frequency intensity. And furthermore, to help you, the adiabaticity parameter depends on the square of the Rabi frequency as well. So once you pass the threshold, this thing is going to work, and it will work well. So that's one argument. And part of the background of this semi-classical trajectory approach was to simulate this with wave packets. Some way back in time, simulating this actually in a molecular physics context, but it transplants very nicely into cold atom physics, and sending wave packets up into coupling regions and seeing that Landau-Zener was obeyed. And what's more, you could even put a wave packet in the gap here and see that it could be trapped if the Rabi frequency was high enough. And this is the effect of the trapping of this wave packet as it goes through the crossing and down again. So that's one approach to why it works. But it relies on classical trajectories and approximations of wave packets going through. So another approach to why it works is to look at the Hamiltonian. So here's the full Hamiltonian for the system, with kinetic energy, with magnetic field interaction, with RF interaction, which is oscillating, and even a bit of gravity thrown in here. And what you can do to get the dressed approach and the dressed basis is to diagonalize this, not paying any particular attention to the kinetic energy term. And when you do that, a side effect of diagonalizing everything else, the potential, if you like, even though it's time dependent, when you diagonalize all of that, then as a result, you get this extra term in the momentum operator here, which behaves a bit like a vector potential. It can be cast into that form. And this is the bit that if you say the dress states are working well, then you neglect this term. And lo and behold, at this point, we have this square root of detuning squared plus Rabi frequency squared that we saw in the talk of Romain Debussy a few days ago. And also some other talks along with the gravity term here. So this is the new Hamiltonian. And then it's straightforward to say, well, okay, if the dress states are very good, then we can find out corrections to that by considering this vector potential as a perturbation in the system. And so you can do perturbation theory, but in the dressed basis, not in the original bare basis. So you do the perturbation theory here. And get the couplings of A dot P and A squared type couplings between the dress states to see how will the dress states leak a bit and to do the detail of that. And we did that a couple of years ago, but this is really looking at the, we use Fermi's golden rule to do this perturbation theory, and the A dot P and A squared terms, a coupling between vibrational states, airy functions, which are vibrational states on an MF equals 0 and F equals 1 manifold. So you have airy function vibrational states here, which are coupled to harmonic oscillator eigenstates belonging to the dress trap over here. And by evaluating those couplings and using Fermi's golden rule, or even more sophisticated things, you can work out how these traps decay. And we did that. So we deliberately, as an experiment, or Helene did in Paris, as an experiment, degraded her RF trap to force it to leak, so hence rather low Rabi frequencies here. And by forcing it to leak, then you can get a leakage of atoms, which can be predicted according to theory. And we got a moderately reasonable fit between the decay of the dress trap when you degraded it and reduced the Rabi frequency. So that was my bit about sort of nuts and bolts underneath the hood of the dressed theory. Now, this picture that I started with is rather simple. The reality is pretty much as Wolf and others have explained it, that you don't tend to use magnetic traps like this, which are linear Zeeman effect as a function of space, but you typically have some kind of quadratic behavior for a magnetic trap. And then you put on your RF, you have resonance over here, and then you get your adiabatic potentials here, which we've now seen, why they are good adiabatic potentials, and you transfer your atoms into the shell state. And essentially here you have a shell in 3D, as was already explained. And this is one of our shells, but looking at it from the point of view of dressing a Yoffie-Pritchard trap rather than, say, the quadrupole trap that Romain was talking about the other day. So when you have that, of course, you have gravity acting on this system. And so our initial prediction back in 2001 for what would happen was that the atoms would collect at the bottom, depending on the orientation of the bubble shell trap. It will either be here or it could be at the bottom over here. And when that was realized a few years later by Helene Perrin, then that's exactly what we saw. And so, this collection at the bottom, the pooling at the bottom of the trap is exactly what you're seeing in this image at one RF frequency and another RF frequency, which makes the trap have a bigger radius effectively and makes it flatter over here. And this is the sort of thing that they are spinning. It's different experimental equipment now, but this is the sort of thing that they are spinning up, as Romain was talking about the other day. But what about the actual bubbles then? So let's say a few quick words about the bubble system. So back in 2001, we had no idea that it would actually be possible to see the bubbles, at least not the big ones. But now, of course, there is this Gold Atom Laboratory orbiting the Earth on the International Space Station. So it's up there. It's in one of these racks. In fact, I have a better picture in a second, I think. And that was put together actually well after 2001, so more or less starting the project in 2012. Supposed to be finished in, let's say, 2020 originally. It wasn't launched in 17, it was launched in 2018. It's not going to finish right now, it's being extended. They're going to fly up more modifications. There's already been some modifications. It's going to be improved. And eventually, when it is replaced, so far beyond this intended mission, and it will be replaced with BCAL, which is a next generation of Bose-Einstein condensate machine and Cold Atom Laboratory. So that's up there. I don't think I need to explain after the talks we've heard, why we would be interested in the bubbles. But yes, vortices have already been discussed. We've had a talk about vortex dynamics on curved surfaces. The group of Selasnech have been interested in condensation temperature on spherical bubble shells and so on. I, in the past, was interested in matter wave interference, still am, and there can be many other points of interest for doing meta-wave bubbles in space. This is the actual cold atom laboratory of the International Space Station. It's actually here in this rack at about this point, and it's very unfortunate in my view that it's right next to the exercise machine, because the exercise machine is going to, well, it would cause a lot of, I think it would cause a lot of trouble, but the experiments tend to be done when the astronauts are sleeping anyway, so they are not active and shaking the space station. These were some preliminary results from the cold atom experiment, trying to make matter wave bubbles. And what you see here is this increasing radio frequencies, and pretty much as we saw on Helene Perrin's experimental results, but more of them. And the point is, as the frequency increases, you expand the bubble. So it's sort of getting bigger and bigger as the RF frequency increases, because you move the resonance point to bigger B fields in the system, which makes the shell bigger. And what you see is you do not see a bubble. I mean, there's a hint of a bubble, but you don't see a bubble. So what's the reason for this? Because we're weightless here. There's no gravity, so the atoms should not be sinking to the bottom. And this is a close-up of the kind of results, preliminary results they had. Well, the answer lies to that question lies in the construction of the trap. Here is a picture well before launch of the cold quanta cell here, with an atom chip on top, and you see RF and actually microwave antennae put on here. But the whole thing is a chip, and chips are sort of inherently one-sided. And if we look to the magnetic fields, which is on this picture, then what you see, if you look at the magnetic fields above the chip surface can be down here. Actually, is this one. This has got Z going in the vertical axis. So the chip can be down here. You see that the gradient in magnetic fields, this is the magnetic trap without any dressing. The gradient is much higher here, closer to the chip than it is over here. And as a result, if I go back to this picture, even if we do a calculation, Grozdevievsky equation with the chip fields and so on, we will find that it's quite tricky to get bubbles unless you would have very large numbers of atoms. You tend to get a pooling away from the chip surface, and it's just due to this gradient effect. Maybe we see it more clearly on this picture, which shows all the relevant potentials. So here we have the potential from the magnetic field, and you see that it's steeper over here than it is over here. The minimum is here. This is even what the Rabi frequency is doing. As you go away from the coil, it's diminishing. So there's got lots of wobbly, spatially varying effects. When you consider the dress states, we have this complex structure. And if you look at these minima in the dressed potential of interest after diagonalizing everything, then you will find it's zoomed in here that there's an energy level difference between the two minima and slight differences in the two shapes. And so because of that, the atoms are going to go further away from the chip where you have the lower minima, which is partly to do with reduced Rabi frequency and to do with the gradient effect. So what can we do about that? Well, we've found an answer potentially, which is to use the microwave loop to introduce microwave energy level shifts. So the microwave loop is also one-sided. It's on one side of the chip with the atoms underneath. And so the microwave fields are going to be asymmetric. They will be diminishing as you go from the center of the magnetic trap, either further north or further south, so to speak, from the trap. So then we do detailed modeling of the chip arrangement. So here we see the conductors and the various coils and the atom cloud, changing polarizations of both radio frequency and microwave frequency. I just mean to say that this is rather complicated, and the paper has been in the works for a little while, but should be coming out very soon, as there's just an appendix to finalize at the moment. So we add in the microwave field. We do a lot of simulations to find the optimum parameters. So here you see, as a function, let's say, of microwave detuning, all the double well potentials that are cross-section through the bubble, if you like, and we find the most symmetrical one. It's probably in this region over here by adjusting all the parameters of the system. And when we do that, we get improved bubbles. So the best one is down here. So these four pictures cover different RF detunings. That means different size bubbles and different RF powers. So you can see there's a tendency to have a better, more uniform bubble when you go to lower RF power and lower detuning. And compare that to before. If I go back maybe too far back. Over here, you see that this is very asymmetric, highly asymmetric, and the whole situation is generally improved, which means you can live with lower atom numbers and still try and get a bubble shape in there. So this paper is nearly finished. It would have been done already on the space station, but there's some electronic problem with the microwave amplifier. But hopefully this, let's hope that it gets tested soon, if this can provide a correction. So now I'll change topic slightly, but you'll see why in a second, and I hope I'm doing okay for time on this. You might be thinking, why am I going to talk about electrons? Why am I going to talk about Stern-Gerlach? And
10 minutes, Barry. 10
okay,
minutes.
Why am I doing that? Well, you'll see why in a second. So this story goes back to, it's a question really, and it's a long argument between, especially between Bohr and Pauli, but also involving other people like Mott and Casimir. All the active guys in quantum physics were, they were guys in those days, I suppose, mostly, were discussing this problem or question of, can you do a Stern-Gerlach spin splitting with electrons? And a number of them put the problem in different ways. I think Pauli put it very nicely. Bohr put it quite verbosely, but the problem basically was that the electron, although it has a magnetic moment and can be split by Stern-Gerlach equipment, also has charge, and the Lorentz force kind of mess up the whole splitting process. And we reviewed this this question in our article back in 2002 from a historical point of view, because we did a technical paper and found out that there was this huge history to the problem, which was actually rather interesting. And this is very early in the development of quantum physics, 1929. I chose this picture because, which is from the Niels Bohr archive, because this is actually contemporary to when they were having these discussions. And I have to say, Pauli looks very, very young guy here. So that's encouraging to people. So in our paper, the work which came before that review, we were looking at splitting of spin states, polarization of the electron beam, if you like, and what it amounts to in the end, because I'm not in the time available going to present the details, although it's an interesting enrichment exercise to discuss it, but I won't do that. What we find is that by shaping the wave packet, essentially squeezing it in the transverse beam directions, called Y and Z here, then placing it in the magnetic field in a special place, you can get splitting, which goes very neatly and separates the electron wave packets from each other. And you see one wave packet split going up here and one split down here with a gradient in the other direction. So this is the sort of diagram of splitting. When you actually run this, you find that that doesn't happen. So we carefully chose wave packet widths and so on to fit. Let me zoom in here. And you see this is the initial wave packet. And then after some time, actually one of the wave packets is still in the same place. And the other wave packet has gone zooming off and has split. So they did split, but this one did not go in the direction expected. Now, we noted all this in the paper back in those days. And what was the reason for that? It was very strange. Well, I go back to this picture of this, we call this the cyclotron line. So it's really kind of a minimum potential. And because I didn't have time to draw the real potential, I've added here what the potential looks like locally to this minimum. And essentially you have these troughs, but with a harmonic frequency, a transverse harmonic frequency, which is varying as you go down this trajectory that you would like to go down. If it was a classical particle, it would just roll down here and go out. At least the lower component would. And what was happening was exactly this thing that was mentioned earlier in the meeting. I think Romain was mentioning it, which is that the energy of the ground vibrational state in these transverse harmonic oscillators is playing a role. And basically, because this is a higher frequency here, it means the ground state energy has gone up. And as a result, the wave packet is kind of got a resisting force to it moving in that direction. And actually the numbers turn out to exactly hold it roughly in its current position. And meanwhile, the lower one is accelerated out by this thing. So it's the transverse ground state energy, the effect of that on the longitudinal motion, which I always found amazing, that because it seems kind of strange to me that something that's happening in the transverse direction is affecting the dynamics rather directly in the longitudinal direction. But nevertheless, this was tested very carefully with 2D wave packet simulations, and that was confirmed. So that's just to take the benefit of hindsight on Romain's talk and say that yes, this effect is known about, that if you talk about a bubble like this, or like the bubble that Romain had, then the fact that if you have varying Rabi frequency, then the transverse frequency of vibration here, you still might be good for 2D gas or something, but you will find that because of that, there will be a small effect on energy. We think that for our bubbles in the space station, that this effect will be too small compared to the other problems that we've got and are correcting for, but it could be in some delicate situations an important effect still. So that was a comment about that. So I need to check how much time I've got left.
5 minutes.
5. Okay, thanks. That's good. So I won't spend too much time on ring traps then, because we heard a bit already. We had our own idea for taking an RF eggshell, a bit like this one, and adding a Bluetooth light sheets, a pair of them, to trap to make a sort of sandwich of atoms in between them, and then making a ring trap that way. That is one approach that's been done. You can even do it with gravity in one Bluetooth light sheet, as Helene did in Paris, and also as Chris Foote did in Oxford. There are a lot of these experiments now, and of course Wolf von Klitzing has already talked about the time average adiabatic potentials. So I won't say anything about that, except to say that I'm always amazed that he makes such huge matter wave rings. This one was 2 millimeters in diameter already in 2017, and then in 2019 we had the beginnings of these accelerating rings. So I look forward to, after 1719, the pattern says the next huge thing should be in 2021, I think. Now there was a question that could you make I've talked about rings, I've talked about shells, could you make a torus? And I think the answer is yes. I had this in my stack of slides from some time ago. So Fernholz in 2007, Fernholz and colleagues had proposed this experiment for making toroidal surfaces. So people who are interested in that geometry, there is a chance I'd check out the paper for the details. But basically, it consists of having a static magnetic material here that makes a quadrupole field above these magnetic rings. The quadrupole field is now wrapped around, the axis of the quadrupole is going around the ring above the surface of the atom chip. Of course, there will be a zero in the middle, but because you apply radio frequency dressing, the atoms are not located in the middle, but are located at some resonant region in a circle or something similar around the dreaded zero, where you get the Majorana spin flips. And so the atoms can be put on the torus. You have to be careful about the radio frequency polarization, but he takes care of that by having current carrying rings for RF above and below this, and putting them out of phase to get a circular polarization where the axis of the polarization is actually rotating as you go around the ring, if you follow what I'm saying. It really needs a bit of an animation perhaps to show that, but the polarization is always the same, going around the ring relative to your local position. And mostly he's interested in having elliptical polarization, because then he can make a double ring trap. And he has an experiment which I think he's been constructing now. I'm not quite sure the current status, but it's supposed to be a double ring experiment. But if he gets the polarization exactly circular, then I do believe he can make a torus out of that. So I think that geometry can be added to the list of interesting geometries. So very quickly then, I just mention a little side project of ours. It's not dependent particularly on RF ring traps, but we're looking a little bit into expanding ring systems. So I don't know if this animation works that Andrew's done here, but I do find this very fascinating. There's some published work already. I've noticed Malcolm Bosch's work, for example, about what happens with these, and we've seen cases with angular momentum even during this conference. My angle here is just to try and look for analytic approximations for what's going on, to understand better the fringe structure, the size of this object. If you think of Wolfgang-Pfitzing's 2mm scale rings, you know, to understand better about how we can deal with coherence in those with or without angular momentum. So if there's anyone out there who's interested in telling me, you know, what could be interesting about this kind of calculation, I would be interested to hear about that in order to choose a good direction for things. So Andrew, my PhD student Andrew, has been calculating these things, and this is a top view of that ring system, and this is another animation with a top view and a cross-sectional view. So in principle, I think people are aware of these things, but notice that this is coming from our analytic expansion, which seems to work quite well. You start to see these beautiful interference fringes, which essentially we've seen some of these earlier in the meeting, but they're very interesting. And the development of this central column is very interesting to my mind, anyway. And our analytic solutions have been compared to let me jump to that one, to numerical solutions, actually, because we may use it for other things. We've used full three-dimensional Schrödinger equation numerical solutions, and that you can see here that the fidelity is very high, and interestingly improves a bit before degrading for quite large times. So that seems to be going very well. Well, I'm worried about the time. I just mentioned briefly that, you know, all this was radio frequency, and then not particularly in the last slide, we have done a couple of years back now, making these cold atom circuits, which can have arbitrary shapes, which is based on microwave dressing, where the trick is, I just mentioned this very quickly, the trick is to have a conductor with the shape you're interested in here, and then you apply microwave to this loop. It has to be a loop, and then the induced currents in the conductor combined with the applied field make a waveguide near to the conductor, which means that you can imprint, if you take a chip approach, an arbitrary kind of shape of this kind. We were very interested in what happens with double loops at the time. And the double loops can look like this, with the waveguides going around here. And when it comes close together, they can just come close together, or they can actually go through each other, or you can get a third loop generated. So you get 3 loops in this case. And we haven't actually taken this further to look at what happens with like 3 big loops and more complex structures, but maybe that should be done. I would be interested to hear from any experimentalist interested in working on with us on that. So this is more or less the slide I had at the beginning, so I can wind down now. So we briefly saw that. We've seen about the matter wave shells. I didn't talk about, you know, having shell, you know, using multiple RF to have concentric shells, which could be done and also could be done in space. Briefly mentioned the ring expansion. I didn't talk about the quantum technology applications, especially this induction, microwave induction scheme might be of interest to making, you know, very small vacuum chambers where you don't want leads going in or out, because it was based on induction. So we had a bit of work on that. And I haven't talked about lattices either, you know, where we can have potential for addressing of lattice sites. And I could imagine actually in a limited way being able to write atomtronic circuits, you know, if instead of having trapping potentials here, you could weaken these lattice sites and maybe join them together. And all this network of wires allows addressing, but you could actually connect them up and have tunneling or whatever between the sides. It's a possibility in that geometry. So there I'm going to finish, just you know, basically with it, saying there are a lot of these topologies and it's interesting. And I just acknowledge collaborators, some of whom are here, and especially Herman Sinoko, who's now left Sussex and is working with Durham, and Andrew Elborn, who's a PhD student at Sussex, and everyone else who's been involved in this work over the years. And there I finish.
Thank you very much, Barry.
Thank you.
So let's see if there are questions. So we have a first question by Gerhard. So Gerhard, please.
Thanks for the wonderful talk. I was wondering if you spend half a minute on telling us about the quantum technology applications you were advertising at the end.
But I think you said, could I say more about the quantum technology applications? So, I mean, the focus of my interest in applying this to quantum technology was on the induction trap. Now, actually, I don't think I have the slide here anymore. Essentially, the idea was to not use this kind of fancy, interesting shape, but to use a perfect ring or good enough ring here, and to use the microwave induction with that. And then you could surround this with a small vacuum chamber. And originally in the quantum technology hubs, we were developing, you know, like centimeter scale vacuum chambers with built-in getter and atom source, everything sort of done in miniature for a sort of portable thing. And there was an idea here to make, for example, some kind of gyroscope using this device. But we had to think carefully about, you know, how could we design the microwave antenna in this case, you know, which had to be outside the vacuum chamber, otherwise there's no advantage in using this scheme. And the best way to choose that for the frequency that we had, bearing in mind that people tend to like working at certain telecoms type microwave frequencies, and bearing in mind that we want to keep it small, we can't have a big antenna and so on. So we did come up with the details of those aspects, the atomic physics, and the microwave antenna, and that still exists. But maybe unfortunately there's a bit of a setback in the vacuum chambers within the development that was going on, so it didn't actually get realized at that point in time. But the idea would be to put atoms into the circular waveguide and do a kind of split, you know, divide, recombine, a little bit like Malcolm Bosher is doing with his linear trap, but this was designed for a ring trap. That was the idea that I was working on.
Good, thanks.
Okay, so then there is a question from Malcolm.
Yeah, hi Barry.
Hi, Malcolm.
I'm intrigued by your analytic model for the expansion of the ring. So,
oh, good.
So what range of interaction strengths does that work for?
So what I showed you was a single atom best. But I haven't put it in the talk. We have done fidelity to Gross-Pilievsky equation, the results from that, and it actually was working rather well. And I'm not quite sure right now off the top of my head. It could have been that, you know, we were doing quite large rings, and therefore the atom density is low for a given number of atoms, and therefore the nonlinear effects are rather low. But the early test was promising with you know, comparing our analytic solution, which is really based on a single atom approach to Gross-Pilievsky. Yeah, I mean, happy to talk about that further with you offline if you're interested in that.
Definitely.
Okay.
So then I propose to thank Barry. So thank you very much, and we can move on to the next speaker.